Thank you. So my name is Pontus. I am an engineer here at Neo4j. I work in one of the Cypher teams, working on the Cypher runtime. And the topic for today's session is the Cypher Parallel Runtime. So almost exactly 1 year ago, at the Node 2023, we launched the what was then the new Parallel Runtime. And a year has passed, and we have been very happy with the release. Overall, it's been going pretty smooth. We've heard very many nice stories from users that they have significantly sped up queries. And if we look at usage, this is data coming from Aura. We see that there is a nice uptick in usage of the parallel runtime, both in the enterprise and the professional tier. However, if we look at the data in a slightly different way, so this is this data coming from the same source, Aura data, but now we see the sort of fraction of usage compared to the default runtime. We see that it's still just a tiny bit of queries that are actually run with the parallel runtime. We would like this number to go up. For one, we like what we've done. We're proud of our parallel runtime, and we also think that users may miss out on a nice performance boost. So the sort of goal of this session is to shamelessly plug the parallel runtime and make sure this at next year's nodes we can have higher usage numbers. So what is this parallel runtime? So it's a fully parallel version of the default runtime we have. It's not something you get by default, hence the low relative usage of it. You have to demand it for each query where you want to use it. It's available everywhere, both self-managed and Aura. And as I said, it's not a default runtime. You have to select it per query. And there are some limitations. You can't use it for all queries. There are some cases where it makes better sense to use the standard runtime. So what we're trying to achieve with this new, it's not that new anymore, it's a year old, but it is that historically Neo4j has been really good at achieving concurrency by having multiple queries running at the same time. You have your thousands or 10,000 queries running at the same time, and in that way you can achieve nice concurrent workloads. But if your the scenario you're looking at is different, and you have one single query and you have a big server with an abundance of CPUs, and you want to run this single query, then historically and traditionally, like by default, Neo4j will only use one thread for that query, and all of the other CPUs will just sit idly waiting for something to do. So the parallel runtime is trying to bridge this gap by having one query running on multiple threads. So this targets what we refer to as analytical queries. It's a bit of a thorny subject, what that is, but basically you can think of it as everything that is a bit slower, longer running, touching more nodes in the graph, things like that. And not just your super fast find one thing from an index and return it. And we only target for now read-only queries and transactions, so you cannot update the graph with the parallel runtime. So that's one of the limitations. So this is where the inspiration for the architecture comes from. And in order to understand how this complicated pipe system can translate into a runtime, we have to first take a step back and just have a sort of query engine 101, trying to understand how the runtime fits into the overall Neo4j server. So the life cycle of a query, it starts with a query text, which is this declarative thing, is a Cypher string, which tells you what you want. Like you want all nodes with some label and related to something else. then that query goes through a series of steps. It checks that it's a valid query, and we check that it's semantically valid, and that it doesn't contain any errors, things like that. And then it's sent to the planner, and the planner tries to find a near optimal plan. And the plan is now something like a recipe, what to do, how to solve this query. And this, like what indexes to use, should we do a scan for a label, should we use an index, things like that. Once we have a logical plan, the runtime takes over. So that's where we sit, and that's where the parallel runtime sits. It takes this logical plan. We will see some examples of logical plans later, and it's trying to execute them on as many CPUs as possible and as fast as possible, and of course correctly. So if we look at the query, the first thing to notice here is the first line, the Cypher runtime equals parallel. So this is how you opt in to use the parallel runtime. This is all the configuration you need. If you have that string, you will be using the parallel runtime. If not, you will not use it. And this query is, the detail is not that important. It's counting the stations or stops between a station called Denmark Hill and Clapham Junction. And if you run this with explain, or if you use the text representation of the plan in browser or similar tools, you will see something like this. I will not, it may look complicated, but we can look at the bottom left. We have this label scan, which is finding a station, and then it has a filter, and it's filtering out all labels with some name. So this is probably Denmark Hill or Clapham Junction. I'm not completely sure. And we see on the right, there is a pipeline column, and we see that there are 7 different pipelines, 0 to 6. So this is where the complicated system of pipes comes in. So what the runtime does is that it turns this logical plan tree into what we call an execution graph, where these pipelines or pipes are the independent units of the query. And in between, we have what we call buffers, and then the data flows in what we call morsel, which are these depicted as these little brown boxes here. So that's the data. The query will start executing at the first pipeline, like pipeline 0 in this case. It will scan for some station, it will filter out the station with the correct name, and then it will, once it has filled up this little box of data, it will pass it to the buffer, and then the next pipeline can pick it up. And then that way data can flow from left to right in the execution graph. In this case, we were counting the number of stations. So there is, and we can't really execute the last pipeline, which is what actually will submit the result back to the client or user. And we can't really do that until since this is accounting, we must count it all. So we have what we call an aggregation boundary before the last pipeline. So there we have to wait until everything is done, and then finally we can execute the last one. So how this works in parallel. So if you squint a little, maybe now you can almost see the pipe system I showed before, if you have a good imagination, that is. So in this example, we have 4 threads, A, B, C, D. So what will happen is that we can immediately start with first pipeline, the 0, and we can execute that on all available threads. Once one of them is done, we can either continue with the first pipeline, or we can jump to the next one. And when the next one has filled up a morsel, there will be work available for the pipeline 2, and so on and so forth. In that way, as the query executes, there will be more and more opportunities to run things in parallel, just until you hit this aggregation boundary, where we have to wait until we have actually counted all the stations in this case. And this is a slide I showed actually last year as well. So if we run this, all our internal benchmark queries with this new runtime, the parallel runtime, and compared it with the default, and then we divide it into 4 groups, we just invent 4 categories. We have fast queries, which are sub-milliseconds, and we have this medium queries, which is 1 to 100 milliseconds, and we have slow queries, which are 100 to 1 second, and everything above that is we call just very slow. So this is, in one way, it sort of goes from non-analytical queries to more analytical queries, if that's even a thing. But what we can see is that for the super fast queries, on the x-axis we see here the speed up. So a speed up of 1 means that it's exactly the same, and -1 is also roughly the same. So the more the data is skewed to the right, the better performance for the parallel runtime. So we see that for super fast queries, the performance is not that good. The default runtime is a saner option, but after that, it's at worst on par in general, and in a lot of cases it's a lot faster. Like for the very slow queries, there are a lot of queries that are 5 to 6 times faster. And we also last year looked at these how it scales with CPUs. So this is a Stack Overflow data set where we have different queries. On the x-axis you have different queries, and on the y-axis you have latency here. And in blue we see results from the default runtime on 8 CPUs, and then in red you have the parallel runtime on 8 CPUs, and then you have increasing CPU count. You have yellow is 16, and then you have 32, 48, 64, and 96 CPUs. This is hard to see. I will switch to log scale, but you see already at 8 CPUs, you see a big boost using the parallel runtime. And if we look at it closer, we see that in most cases we see a nice sort of almost linear increase, so that the more cores you provide, the faster the query runs. However, we saw a few instances of this type of behavior, and this is where we were at last year's notes. Mostly it worked fine, it was better, but in some cases we saw this pattern emerge, that we saw a speed up to some CPU count, but at even higher CPU counts than it was either not improving anymore, or we even saw a degradation in performance by adding CPUs. So this is a problem we have been working hard to try to solve during the year. So in general, the performance scales nice with the number of CPUs. However, there are cases where more CPUs make performance worse. So the first solution to this is that we need a tool to sort of need to introspect what each thread in the system is doing. And then once we know what it's doing or not doing, we have to make sure that we can keep all the threads in the system busy. So if we look at one query where we could see this is just a simple query with a variable length pattern here, and you match some user that is related by posted or answered in sort of a multi-step fashion. The plan here is, this is how the plan looked last year. It's not that interesting, but we can note that it has this var length in the middle of the plan in pipeline 2. And we created this tool so that we can monitor what each thread was up to. And if we run this query using that tool, this pattern emerge. And this is a little bit hard to see, but what we're basically seeing that it's only using a single thread, this thread 118, and all the other threads of the system are not doing anything. So what happens here is that in this case, this var length is the only thing that, like the heaviest operation. All the other things are quite quick, and then the problem turns into a single-threaded problem, because all work will happen in this var length and everything else will just wait for that to finish. So we solve this by implementing a form of work stealing, where when we have this situation, other threads can jump in and help out so that we can distribute work more evenly across threads. So running this now with the current version, we see here, it's still hard to see, but you see that there are lots of threads involved now, and there is a much nicer and even distribution of work among the threads. And if we look at performance, we see here in blue how it looked last year, and in red the current state of things. This is running on 16 CPUs. But this wasn't the only scaling problem we had. We also could end up with a form of thread starvation. For example, queries like this, where you have a subquery like this. This is where not exist, and then you have a subquery in there. You often get this anti here. The plan is not super important, but this anti here was something we discovered that in a lot of cases where this happened, we had these types of plans. And if we ran this with this new fancy tool of ours, this is the pattern that emerged. So we see that initially it looks fine. It's well spread, like work is spread across all the threads, but something happens at 1.5 seconds here. And after that, only one thread at a time sort of gets to do any work. So we see that it can jump between threads, but it's mostly one thread at a time. And we here see the 2-second mark, and the query will finish after something like, I think it's 6.5 seconds or something like that. But the last 5.5 seconds is just one thread at a time. So running the same query in the current version, we don't see that much different. We see now we have this partition node by label scan explicitly, but that is not helping much for scaling. What we did do is that we discovered that it was indeed this anti, and that created a problem with scheduling, so that work was not, it was hard for the other work to be picked up, so that it wasn't like evenly distributed. So by fixing these scaling issues, and when we run the same query now, we see the 2-second mark. This is hard to see the x-axis, but we see the 2-second mark, which was roughly where it turned single-threaded before, and it now finishes. And here we see that all threads are busy working on the query. And looking at the performance, here we see in blue is how it looked last year, and in red it's how it looks now. And this is running this query on 8, 16, 32, and 64 CPUs. We see there last year's results. We see that it speeds up going from 8 to 16, but then further increasing the CPU count is actually detrimental to performance. It gets worse from 16 to 32, and even worse going to 64 CPUs. But in red, we see that the results continue to go faster with adding more CPUs, which is nice. But adding CPUs shouldn't hurt your performance. So we're very happy with that. We had them for a couple of other smaller problems. We noticed that some common aggregation are not as fast as they should be. We also saw some common leaf operators aren't parallelized as they should. And sometimes we saw that memory usage is not as good as we think it would do. And we could solve this we have improved some of the aggregations in the parallel runtime. We will see a slide on that soon. We also introduced new dedicated partitioned operators that can work across threads. And we also have worked on reusing these more. So these big chunks of data instead of creating new ones, we can keep them and reuse them, which will lead to a lower memory pressure. So for aggregations, so this is a pattern we saw occurring often, which is a type of aggregation. In this case, you want the percentile of different, like the 0th, 10th, 20th percentile of some data. And in last year, you would see a plan like this. The difference is not super obvious, but you can see that in the aggregation, we now have this percentiles. We rewrite this internally to a more efficient version of this function so that we can execute it faster. And looking at results, we see the same thing. It's a lot faster now than it used to be. So blue is last year, red is now. And we also introduced a new operator for another commonly occurring pattern is when you look for labels which has one label but not another. So in this case, we're looking for all nodes that are have this post label, but it's not a question. And how we would solve that last year was we would, for example, scan for the post, and then we will filter out everything that's not a question. Now we have introduced a dedicated operator for this, which also is partition, meaning that it can be partitioned across threads. So this will, on each thread, it will find this sort of subtraction between post and questions. And this also shows nice speed ups. So in summary, the parallel runtime is almost always faster. Performance usually scales with the number of CPU. The more, the faster. At worst, it should now be adding CPUs should never be detrimental to performance. And we have also added lots of new improvements since the launch last year. There are still write queries are still not supported. And super fast queries is not. And for those, it still makes more sense to use the default runtime. However, I hope that you will at least try it out, and then maybe next year I can come back and talk about something else. Thank you. I will answer questions afterwards if you have any. And if you have more, if you're curious, there are more information on our in this blog, which you can find from the slides. Thanks.